Hello, welcome to Geology 1020, the Earth Through Time. I'm Dr. Rieger. I look forward to a great course. First want to introduce myself. I said that, my name is Dr. Rieger. I've been a full-time faculty member at CCRI since 2013. I teach geology, oceanography, natural disasters, and physics. And I am also the chair of the Physics and Engineering Department here at CCRI. If you need anything throughout the course, please don't hesitate to send me an email or visit my virtual office hours. So we'll go ahead and get started. The Earth Through Time, this is a historical geology course. We'll talk more about what that means in a little bit, but I have this slide as an introductory slide because it encapsulates a lot about what we'll be talking about this semester. We see this is, if you're not familiar, this is a picture of the Grand Canyon. And if you look closely, you can see that the walls are made up of these layers of rock. Now we'll learn, this is sedimentary rock. And there's all these different layers. You can see on the far side of the canyon, there's a layer there. Now, as you go down into this canyon, you go past different layers of rock. Well, each layer of rock, these layers in geology we call them beds, each bed of rock tells a story about what was happening at that moment in the past, in Earth's history. What were the conditions like? What life was on the planet? What types of living organisms were on the planet? And so by looking at the rock record, which is on beautiful display here in the Grand Canyon, we can gain insight into the history of our planet, which is important because we live here, it is our home, and our history is intimately tied to the history of this planet. So learning the history of our planet, we're in a sense learning part of our own history and learning more about ourselves. So what is geology? Well, geology is the study of Earth and other rocky planets and their moons. So most people think, oh, geologists study the Earth, which is largely the case, but it's not strictly relegated to the Earth. Geologists do study other planets in our solar system. For example, geologists have designed instruments to go aboard rovers that have visited Mars to do geological experiments on the surface of Mars, learn what type of minerals or rocks and so forth are there. So geology is not strictly confined to this planet, though most geologists do focus on this planet for obvious reasons. It is A, the planet of most interest, being that it is our home planet, and B, it is the most accessible planet, also because it's our home planet. But geology is kind of broken down into two pillars. We have physical geology, which is basically concerned with studying what the Earth is made up of, what materials, rocks and minerals are found on Earth, and how they form, and what processes operate on the surface of Earth and beneath the surface of the Earth. So physical geology is basically what is the planet made up of, what is it composed of, and how does it work? Where historical geology, on the other hand, it takes a basic knowledge of physical geology, how the Earth works, and it uses that knowledge and applies it to observations that we make, different rocks, different fossils, and so forth that we find, to come to conclusions about what happened in Earth's past. So it's an historical science, historical geology, where we try to reconstruct or put together a narrative of past events. I like to use the analogy of forensics, right? So forensics, you come to a crime scene, or it doesn't have to be a crime scene, maybe the scene of an accident. You come to some scene, and what you do is you use an understanding of different sciences, say ballistics, or fingerprinting, or You know, some forensics uses entomology, like, you know, what certain insects, you know, it's kind of morbid, but you know, come on a body at different stages, and or looking at blood splatter. All these different sciences, we understand how they work, and then we apply that understanding to what we observe at the scene in order to construct what happened. Right, so that's what historical geology is. We take our understanding of physical geology and apply it to the observations we make on a planet to come to conclusions about what happened in the past and put together a narrative that is Earth's history. And so historical geology is concerned with the origin and evolution of Earth's continents, the oceans, the atmosphere, and life. Right, so it tries to answer some pretty profound questions, you know, historical geology. It's one of the reasons why I find it so fascinating. It's not every day you get to talk about, well, you know, where did the continents come from? Where did the oceans come from? How did life as we know it come to be on this planet? So some pretty fun questions, pretty fun topics. So the Earth is not just a big rock, right? The Earth is a system that has 4 primary components. We have the solid Earth, which is the rocky planet. But we also have what's known as the hydrosphere. That is the water that is both on the surface as a liquid, in the atmosphere as a vapor, and beneath the surface as a liquid. It also includes solid water, ice on the water. Sometimes the ice on the Earth. Sometimes the ice on the Earth is known as the cryosphere. But that's the hydrosphere. Then we have the atmosphere. That is the gases held to Earth's surface by its gravity. Then we have the biosphere. That's the living organisms on the Earth. And then we come back to the solid Earth. And the most important thing is that all 4 of these components are interrelated and they interact with each other. Neither of them is in a vacuum. So what happens in the solid Earth, it impacts the hydrosphere, the atmosphere, the biosphere, and vice versa. Okay? So the Earth system is composed of these 4 different components that are constantly interacting with each other. You know, and so we'll see that throughout the course, that interaction between those 4 components. So how does geology relate to our experience as humans? Well, it has an impact on our daily life, which we'll talk a little bit more about in the next slide. But geology has found its way in the human psyche because, well, first of all, you know, we live on this planet. What happens on this planet and what this planet has to provide significantly shapes our lives. And we can see this impact on geology on humans in our culture. For example, our art. You see, you know, a lot of landscape paintings. We paint landscapes. People describe landscapes or geologic features in poetry. All different types of art. Even song, like Rocky Mountain High, right, Colorado, and so forth. And so it's it's deep seated in us, you know, the Earth, because we are part of the Earth. And so there's a wide range of environmental problems that influence us. We also, the resources the Earth provides influences us. It also dictates military tactics. You know, we hear how geology has influenced the history of military affairs, like Hannibal crossing the Alps, and so forth. And then as we operate as a society, we need this basic understanding of geology, which is important. Because the Earth and the Earth system, not just the solid Earth, it impacts us every single day. You know, we don't experience natural disasters every day, but you know, there are natural disasters occurring in somewhere in the world most days, large or small. And so we're at the mercy of those processes. We're also dependent on the resources that the Earth provides. finite resources. That's something that, you know, sometimes we lose sight of, that these resources are often finite. Some of them are not, but a lot of them are finite, which is important. And that has an impact on economics and politics, right? The cost of goods, the cost of materials or resources depends on how scarce or how abundant they are, where they're located, the ease at which they can be acquired, how much processing needs to be done to get it from raw material to finished good. That all, you know, is dependent on the earth, how those raw materials are allocated and located on the earth. The earth also, in geology, has influence on politics. A lot of political boundaries are shaped by the result of geology. For example, the border of France and Spain is the Pyrenees Mountains. Many state borders in the United States are dictated by the Mississippi River, right, and so forth. So a lot of political boundaries. You know, we look at the map of the world. The map of the world is largely influenced by the geology. Geology influences us when we make decisions, right? The decisions we make are important as a consumer and both a citizen. So what we purchase, you know, we should have geology in mind. So if we purchase something that is, you know, just disposable, one-use disposable, the piece of plastic that's going to go in a landfill and sit there for hundreds of years, we should know what impact that's going to have on the planet. Or, you know, if we burn fossil fuels or if we do other things, we have to have an understanding of how our actions as consumers influences the earth, because, we said before, we're part of the biosphere, and we influence the earth, earth influences us back. Also, we have to have an understanding of geology. We make decisions as citizens. When we elect people, that are going to keep our environment's interest in mind, as well as other interests. So mainly so that as a society, we can move forward in the future in a sustainable way. So whenever we develop our society moving forward, we do so in a way that works harmoniously with our environment, with the Earth system, that's not at odds. Because whenever we develop in a way that's not sustainable, whenever we develop in a way that has a negative impact on the Earth system, what we're really doing is we're just borrowing against the future. And eventually it's going to come back, and we're going to have to pay that debt in some way or another. You know, we're going to have to deal with that landfill. We're going to have to deal with the warming. We're going to have to, you know, someone in the future is going to have to deal with that. It's not going to go away overnight. So whenever we do things in unsustainable ways, it's going to come back at some point in time. This figure on the right is this little baby. It's surrounded with different natural resources, and the amounts listed above each resource is the average amount of each resource that an American consumes in one lifetime. Now, some of these resources, natural resources, are more obvious than others. For example, petroleum, right? Most of you, I'm sure, know that gasoline comes from petroleum. It's a derivative of petroleum. And so the average American consumes, and when I say consume, I mean in the economic sense, where you consume a good is to use it, and that no one else can use that good after you've used it, not in a literal sense where you put it in your mouth and swallow it. So the economic sense of consume, the average American consumes 274,000 liters of petroleum. So that's a lot of gasoline, but we just don't use petroleum for gasoline. We use petroleum in a lot of products. A very common one is plastics. So plastics are also derived from petroleum or crude oil. Natural gas. Some people use natural gas to heat their homes. We also use a lot of natural gas to generate electricity at power plants, also with coal. So most of our electricity is generated using natural gas and coal. So if you have a light on, the electricity running through your computer, all that, most of that electricity was likely generated by the burning of either natural gas or coal, both fossil fuels. Copper, copper we find a lot in plumbing and pipes. We also find copper in electronics in cords and in circuit boards. Gold, we find gold in obviously jewelry, also find gold in electronics and medical applications. Stone, sand, and gravel, well, that's a lot of stone, sand, and gravel, almost, almost 500,000 kilograms. Did you use that much stone, sand, and gravel? Do you think you'll use that much in your lifetime? Well, we use this communally, right? When we build the infrastructure of our society, roads and bridges and buildings, we use stone, sand, and gravel as construction materials. And as we use them, so every time you, for example, drive down the road, the road is incurring somewhere, right? So you have used or consumed a tiny portion of that road every time you use it, right? So in the end, an average American uses about that much stone, sand, and gravel. Also, another construction material is cement. We use iron ore and aluminum ore, bauxite. We use those. Those are minerals that we smelt to extract the metals, iron and aluminum, to make steel or aluminum for the frames of our buildings or the frames of our cars or bicycles and so forth. And so there's a lot of materials here that we are dependent upon every single day. From the moment we wake up, we're constantly depending on materials that are sourced from natural resources that come from the earth. Now, it's easy for us to lose sight of that today, especially because we're so far removed from this due to the the supply chain and production chain of goods, that we don't really notice. We're not really cognizant of the sourcing of the materials that our goods come from. But maybe 150, 200 years ago, if you wanted a toothbrush, that toothbrush had to be made out of wood or metal or a piece of whalebone or something. So you have a raw, less processed, more raw good in your hands. You're more conscious of where that toothbrush came from. And where today they just turn them out of a factory, and we lose sight of that. But we are dependent. That stuff that's in our goods and our products, it has to come from somewhere. It comes from the earth. So to understand the planet, where do we go? Where do we start to understand Earth? Well, we have to go to the beginning. But where is the beginning of Earth? Right? Because we know to fully understand something, we have to go to its origins. We know that from every superhero comic, right? Every superhero, every hero has an origin story to really understand where this character comes from. The same is true for the Earth and everything else. Right, so what is the origin of planet Earth? Where did Earth come from? Well, we go far enough back, the very beginning, at least to the extent of our knowledge, it goes back to the Big Bang. Okay, so what is the Big Bang? Well, it's a theory. It's called the Big Bang Theory. And the Big Bang Theory, the title of the slide is a little bit misleading. It doesn't describe the origin of the universe. We don't know where the universe came from. We don't know how the universe came to be. We don't know the answers to those questions. What the Big Bang Theory does is it provides an explanation to the early moments of the universe and how it changed or evolved after those early moments. Okay. And so according to this theory, the Big Bang is this moment in time where the universe, which was 13.7 billion years ago, contracted to a tiny point called a singularity. So the entire universe, all the matter and energy, space and time that is inside the universe, was contracted to a point. Extremely dense, hot body of matter and energy. And the Big Bang is the rapid expansion of the universe into, well, we don't know what it's expanding into because it's outside the universe, but it was expanding. And that initial rapid expansion of the universe is what's known as the Big Bang. It didn't make a bang, didn't go boom, right? Because that's a sound, and sound needs matter to travel through. It needs a medium to travel through, like air, like gas, like we're a solid. And well, if there's no space, because space, three-dimensional space, is a construct of the universe. If there's no space, then there's no matter can occupy, and so there's no sound, right? So the Big Bang is more of a dramatic name to kind of illustrate this initial rapid expansion. That rapid expansion began 13.7 billion years ago. So it's a long time ago, right? 13.7 billion years ago. What was going on 13.75 billion years ago? We don't know. Science doesn't have an answer for it, right? And even as far as, this whole theory, that's all it is a theory. If tomorrow, we make an observation, the scientific community makes an observation that's in direct conflict with this theory, and it's back to the drawing board, right? This theory has flaws in it and needs to be revised because it cannot explain these new observations. So this is our best working scientific model to explain the early moments of the universe, Big Bang theory. So it is a theory, it's not a hypothesis. That means that there's been scientific observations that support it. And so what evidence is there for the Big Bang? Well, evidence for the idea that the universe is expanding from a central point came from, the evidence we got was from the Hubble telescope. Now, the Hubble telescope was named after Edwin Hubble. Edwin Hubble was an astronomer who thought, if this Big Bang theory is correct, then all the galaxies in the universe should be moving as space expands, as the universe is expanding. So we can use this raisin bread as an analogy, right? So this raisin bread, the dough is the universe, okay? Those the space of the universe. So this is the outer edge of the universe, and all the dough, that's space. The raisins, these are the galaxies embedded in space, the universe. And as the universe expands, space, three-dimensional space in the universe expands with it. And so the raisins move because they're embedded in space, just like these raisins. The galaxies move because they're embedded in the space, just as the raisins move because they're embedded in the dough. And they're moving away from the central point. So you can imagine if you were on one of these raisins, and you can't sense your own motion, right? Because you're moving. But if you looked at other raisins, you would note that the further a raisin is from you, the faster it would appear to be moving away from you, right? So this raisin, because you're moving this way, right? And so it appears that this raisin is not moving away from you very quickly, but this raisin seems to be moving away from you more quickly, and this raisin is moving away from you very quickly. So Edwin Hubble predicted that we would make this observation, that the further a galaxy is from our own, the Milky Way galaxy, the faster it will be traveling away from us. So that was his hypothesis that would, if proven, would help support this Big Bang hypothesis. We eventually finally had the technology to make a telescope that could make those measurements, and they launched it. And as I said, they named it after Edwin Hubble. And sure enough, as he, postulated, that was found to be correct. That the more distant a galaxy is from our own, the faster it's traveling away from us, which acts in support of the idea that the universe is expanding, still to this day, from a central point in which it began expanding. Also, everywhere we point our telescopes, no matter where we look in the night sky, we measure a faint amount of radiation, so a faint amount of energy. Even if there's no known celestial body that's radiating light, that's producing light, or could be reflecting light back, we measure a small amount. This is called the afterglow, or background radiation, and it's thought to be a remnant of the very early moments of the universe where charged particles are moving around very rapidly, and whenever a charged particle accelerates, it speeds up or slows down and changes direction, it emits light, electromagnetic radiation. So there's a bunch of light and energy being created then. As the universe began to spread, expand, the energy was just spreading out within that expanding universe and becoming less and less dense, more and more dilute. And today we see that faint amount of energy everywhere we look, just still floating around in the universe today. So the fact that it's everywhere, it's ubiquitous, suggests that its source is linked to the early moments of the universe, whenever it was confined to a small space. So we've made several, these are just two observations. We made several observations that support this Big Bang theory. So the initial composition of the universe. So initially the universe was about 100% hydrogen and helium. Okay, so hydrogen is the smallest atom, meaning that it has one proton in its nucleus. We'll talk more about, we'll talk a little bit about matter and the structure of matter when we talk about matter and minerals. But hydrogen is the smallest atom, has one proton. Helium is the second smallest atom with 2 protons. So initially, the entire universe was nothing but hydrogen and helium. Now, as the universe continued to expand and cool, matter, in this case, hydrogen and helium, began to condense because matter is attracted to other matter due to gravity. And so big balls of hydrogen began to form, and clusters of and these balls of hydrogen would become stars, and clusters of stars form. And these clusters of stars are galaxies. But in this process of stars forming, what happened is the composition of the universe began to change. Until today, 98% of the universe is still hydrogen and helium, but 2% is all other elements. All other elements that have 3 or more protons in their nucleus, which is most elements you can think of: carbon, nitrogen, oxygen, copper, potassium, calcium, magnesium, sodium, chlorine, gold, you name it, right? All those other elements are in that 2%. They did not originally exist. And it's the formation of stars that brought about their existence. But how so? How did those other elements come to be? What role did stars play in that? Well, to answer that question, to look at the star cycle. So stars are these massive balls of hydrogen. And they're so massive that the gravity produces a pressure inside that's large enough to fuse atoms together. Now, atoms don't like to get too close to each other, so it takes a huge amount of energy to push them really close to each other. But if you have enough energy, enough pressure to do that, if they're pushed close enough, what happens is their nuclei, the centers of them, fuse together, so then 2 atoms will become 1. This process is called nuclear fusion. And the smaller the atoms are, the easier it is to fuse together. So the atom that's easiest to fuse together is hydrogen. Fuse 2 hydrogens together. Since each hydrogen has 1 proton, if you fuse 2 hydrogens together, you get a helium atom with 2 protons in its nucleus. And so because it takes so much pressure and energy to fuse them together, once they are fused together, they release energy. They release a lot of energy, in fact. And that energy that's released by this nuclear fusion is the twinkle of a star, right? It's the light that's emitted from the star. It's not just visible light. There's all different frequencies of light: radio waves, microwaves, infrared, visible light, ultraviolet, gamma rays, X-rays. There's all different types of frequencies of light emitted, right? And so that nuclear fusion that's happening inside the star is basically the fuel of the star. The hydrogen is the fuel of the star. It fuses the hydrogen together, which produces energy, electromagnetic radiation. And that energy that's being emitted and expelled from the star actually helps support the structure of the star. And if that energy wasn't being emitted outward, the star would actually collapse in on itself under its own weight. That, in fact, actually happens. Once the star has fused all of its hydrogen into helium, it now has no more fuel, right? Because it doesn't have the pressure to fuse helium atoms together. what happens is the star begins to implode on itself. And as it implodes and it shrinks, the pressure inside increases dramatically. And it increases to the point where now larger atoms are able to be fused together. And in this relatively short period of time in the stellar cycle, as the star is collapsing, larger elements are formed through nuclear fusion. So all the larger elements in the universe, everything from lithium to uranium, are forged in this time as the star is collapsing. And so much energy is expelled from the formation of these larger atoms that the star explodes. It just blasts into pieces in what's called a supernova. Supernova is the most violent event in the universe, and all those larger atoms that are forged in that collapsing, the dying of the star, are then scattered throughout the universe by the supernova. All right, so fast forward 13.7 billion years ago, there's a lot of stars form, die, forging larger elements together. Fast forward from 13.7 to 4.6 billion years ago. There's a cloud of debris from supernova that have occurred for the last several billion years. And this cloud of debris, it begins to collapse due to gravity, and it's rotating. And because it's rotating, it flattens into a disk as well. So it's this rotating cloud. You see this cloud, and it's rotating. It flattens into a disk. Now what happens is the matter, the material in this cloud, it begins to condense. It begins to aggregate because matter is attracted to other matter due to gravity. And so the lighter elements, they concentrate in the center, and they all collide and condense to form a large ball of hydrogen, which is our sun. Right? And then as you go further out, materials begin to collide and they form the planets. So you can see these planets forming from debris, aggregating, condensing, forming planets. And so this is the formation of our solar system. So the sun forms in the center and the planets form from the disk of debris. So what is the age of the Earth? When did the Earth form? Well, we come to this answer. We look to how the Earth formed from materials aggregating out of that disk of debris in the early solar system. Right? Now, we look at bits of that debris that are still floating around the solar system, asteroids, meteorites, and also elements, rocks from the moon that formed soon after the Earth did. And measuring the age of those materials, so minerals from the moon and meteorites that come to Earth, we find that they date to 4.57 billion years old. So those are the materials, meteorites, that form the Earth. So the Earth can't be any older than the material it's made out of, right? If you look at a house can't be older than the wood it's made out of, right? The wood had to exist first in order for the house to be built out of it. So this puts an upper limit on the age of the Earth. The Earth can't be older than about 4.6 if we round up billion years old. All right, so that kind of says that it can't be any older than that. Then looking on the Earth, the oldest rocks found on the Earth, which are found in northwest Canada, date to about 4.055 billion years old. And the oldest Earth materials, actually individual mineral crystals called zircons from in Australia, sandstones, they date back to 3.7 billion years old. So these are giving us limits that the Earth had to exist by 4.37 billion years ago for those mineral crystals to form on Earth. And it couldn't have existed before 4.57 billion years ago. So it kind of gives us this 0.2 or 200 million year range in which the Earth could have formed, right? And so we generally ascribe the age of the Earth to be about 4.57 billion years old, and people just round to 4.6. So it's commonly said that the Earth is 4.6 billion years old. And so to put this on a timeline, we see down here the oldest solar system materials, all right, which we find from dating, determining the age of meteorites that come to the Earth. And so by 4.54 billion years ago, the Earth existed as a coherent or condensed body. So everything was together. It wasn't no longer a cloud of debris that was forming. It was all together, but it was molten. It was not solid. It was a molten state. And 4.53 billion years ago, there was a nomadic planet named Theia. It was about the size of Mars that collided with Earth and threw off material that would consolidate and form the moon. And 4.5 billion years ago, the Earth had solidified. All right, so the Earth had cooled and solidified in place. And 4.37 billion years ago, that's whenever the oldest known mineral crystals formed. And 4.05 billion years ago, way up here, oldest known rocks formed. So, remember the universe is 13.7 billion years old. The Earth is about 4.6 billion years. That's a long time, a billion years. And I'll have that laid out here. It's 1 and 9 zeros, a billion years. So, it's been here for quite some time. And one thing we're going to learn, what's remarkable, is that animal life, on the other hand, has been here for a relatively short period of time. So the Earth was very old, but life as we know it is actually very young. So the Earth formed from material aggregating, so colliding. So you can imagine a tiny particle of material flying through space and another particle coming and colliding because they're attracted to each other in the gravity, and then they stick together, and then more stuff. So now it's more massive, so it has more gravity, so it pulls in even more stuff. And this snowballing effect occurs. And this snowballing occurs for quite some time, and eventually a planet grows from that process. Now, in that process, these objects are flying at thousands of miles per hour, slamming into this growing planet. So there's a lot of energy involved. Each impact generates a lot of heat. That heat from the impacts, along with heat from radioactive elements, which we'll talk about later in this course, those radioactive elements decaying away, generating heat. That heat is enough to render the planet completely molten. And while in a molten state, it undergoes a process known as density stratification, where the planet separates into layers based upon the density of the materials. The densest materials sink to the center, the densest materials sink down, and the less dense materials rise. And this is how the Earth develops its layered structure that it has. And so in this date, 4.6 billion years, this is pretty much the date we ascribe to the Earth for its age, 4.6 billion years. And how we come to that number is we find rocks on Earth that go up to 4 billion years old, some minerals up to around 4.2 billion years old. Then we look at the asteroids and meteorites that we find in the universe, and they date to around 4.6 billion years old. So we know that the Earth is made up of that debris that's floating around in our solar system, and so the Earth can't be any older than the material it's made up of, and it can't be any younger than the oldest materials found on the planet. So that's how we come to that number. So, and then once again, density stratification is the process of the denser material sinking to the bottom, less dense materials rising to the top, and the Earth layering based upon density. Very similar to Italian dressing, right? How the oil and the water separate and layer. So this is, as I said, how Earth got its layered structure. Imagine you take this mason jar with honey, butter, water, and air, and you shake it up, right? It's all mixed up, and if you sit down on the table, let it sit, eventually it'll separate, right? It'll stratify, Stratify means to layer. Well, stratify based upon density. The densest material, the honey, will sink to the bottom. The next dense, butter, will settle on top of that. And the next densest material, water, and then the least dense on top. With the densest materials at the bottom, which for the Earth, that's the center, and the least dense materials at the top, the outside. That's how Earth gets layered structure. So now we're going to look at the different layers of the Earth. Geologists look at these layers through two different lenses. Look at the chemical layers, which is the layers defined by what they're composed of, what they're made up of. Then we look at the mechanical layers. Now, these are layers defined by their physical properties, how they physically behave. Right? And so we're going to start with the chemical layer. I'm sure most of you have heard of these chemical layers before. They are the core, the mantle, and the crust. We're going to start first the core. It's 16% of Earth's volume. And what makes the core chemically distinct is that it is completely composed of metal, in particular iron. So we have a metallic core. It's about 95% iron, 5% nickel. It's a little dash of nickel in there. But so Earth has a metallic core, mostly of iron. Then outside the core is the mantle. The mantle is 83% of Earth's volume. So the mantle surrounds the core, and unfortunately a lot of figures have the mantle as being red in color. So this layer right here, which when you think red, you see red, you think molten rock. The mantle is not molten rock. It is solid rock. It's composed mostly of a rock called peridotite, which is very dense, which makes sense because, you know, metal is the densest. Then outside the metal is very dense rock. And so peridotite is very rich in metals like iron and magnesium, which makes it very dense. So the mantle is composed of very dense, metal-rich rock. And finally, we have the crust, which is only 1% of Earth's volume. It's the outermost chemical layer, composed of solid rock, and it's metal-poor rock. So it's rock, just like the mantle, but there's much less metal in it, which makes it less dense. And there's two types of crust. There's a thick continental crust that ranges between 20 and 90 kilometers in thickness, mostly composed of a rock called granite, which is a relatively low density rock because it doesn't have a lot of metals such as iron and magnesium in it. Then there's the thinner oceanic crust, which ranges from 5 to 10 kilometers thick, composed of a rock, mostly of a rock called basalt, which is a little bit denser than granite because it has a little bit more iron and magnesium in it, but it's still nothing like the mantle rock, which is much more dense. It has much more iron and magnesium in it. So the crust is metal poor rock. There's two types of crust: thicker continental crust and thinner oceanic crust. So before we look at the mechanical properties of the Earth, first we're going to take a second and talk about how the physical properties of Earth change with depth. In particular, we're going to look at pressure, density, and temperature. So pressure is force over area. So you might have probably heard of pressure before, like atmospheric pressure, or the pressure in your car or bike tire. The pressure, English units of pressure are PSIs, pounds per square inch. Pound is a unit of force, per square inch, unit of area. So pressure is force per area. The SI unit is pascals. That's the unit of pressure in the metric system. And so gigapascals is 1 million, it's 1 billion pascals. And to give you a sense, atmospheric pressure is, I think, 101,000 pascals. So it's 0.1 megapascals. The pressure inside Earth is much, much, much greater than atmospheric pressure. But you can see with depth, this is the x-axis is depth. This is the surface of the Earth. This is going down towards the center of the Earth, right? That's the center of the Earth. This is pressure increasing this way. See, as you go down inside the Earth, the pressure just continuously increases, just like as you swim deeper and deeper underwater, the pressure increases as well. because the pressure is the weight of all the overlying material acting down. So the deeper you go, the more material whose weight is acting down using the greater pressure. Density here, this is interesting, this is density. Density is, well, I forgot to mention it when I talked about density stratification. Density is the amount of mass per given unit of volume of a substance. So in this case, it's measured in grams, which is how much mass per cubic centimeter. So once again, depth is on the x-axis, increasing to the right. So the surface is here, and the center of the Earth is here. And density is increasing this way. You can see that the density increases with Earth too. See this sudden jump in density there? It goes from a little bit more than 5 to about 10 grams per cubic centimeter. Well, why is that huge change in density? Because this is the mantle, and this is the core. This is the core mantle boundary, right? So you're seeing a layer, the boundary between two layers there. And so the core, the metallic core, is much more dense than the rock mantle. Right, so pressure and density both increase with depth, as you can see. And finally, we'll look at temperature. Now this graph is oriented differently, where now depth is on the y-axis, increasing down. This is the surface, and this is the center of the Earth. And temperature in centigrade is increasing on to the right on the x-axis. We see a temperature increases with depth. Right, as you go down, the temperature increases, gets higher and higher and higher. So in Earth, as you go from the surface and go deeper, the pressure increases, the temperature increases, and the density increases. See the temperature inside the planet, it's very hot. The center of the planet is about 4,000 degrees centigrade, which is very warm. Okay. So now that we know that Earth's pressure, temperature, and density increase with depth, we now look at the mechanical layers of the Earth. So these are layers defined by their mechanical properties, and those physical properties, pressure and temperature, they'll play in as we discuss these. So starting from the center and working our way out, like we did with the chemical layers, the innermost mechanical layer is the inner core. So it's part of the chemical layer known as a core. So chemically, it's metal. What makes it mechanically distinct from the rest of the core is that it is solid. So the inner core is solid metal, mostly iron, solid iron. Where the rest of the core, which is a different mechanical layer, known as the outer core, is molten. It's liquid iron. Of importance, this is the only molten or liquid layer in the planet. There is no liquid layer of rock or molten layer of rock. There's only one molten layer, and that is the outer core, and it's molten metal. It serves an important role because this liquid iron, as it moves, the iron atoms have an electrical charge, and their motion generates a magnetic field, and that's the source of the Earth's geomagnetic field, which is important for several reasons. One of the most important is that it helps shield the surface of the Earth from higher energy radiation from the sun, like X-rays and gamma rays. So without that geomagnetic field, the Earth's surface would be bombarded with much higher energy radiation, which could have likely prohibited complex life from evolving on the planet. So outside of the outer core is the mesosphere. Now the mesosphere is makes up the majority of the mantle, the chemical layer known as the mantle. Meso means middle. So this is the middle part of the planet. It's solid rock. As I said, it surrounds the outer core. But because it's deep, it's very hot, has a high temperature, and it's at a large pressure. And because of this, even though it's rock, at these high pressures and temperatures, as I said, even though it's solid rock, it behaves plastically, and it can slowly flow. It can slowly deform. And it does this on geologic timescales. So over the course of millions of years, it can deform and change shape without cracking or breaking or fracturing. And so it can kind of flow. Now I say flow in quotes because it's not flowing like a liquid. It can flow as it can creep, it can deform and change shape without cracking and breaking. And outside of the mesosphere is a much smaller layer, which here you see this little cutout. Up here it's fine. The lower mantle is another name for the mesosphere. And so this is the mesosphere, the uppermost part of the mesosphere. You see this little thin layer here called the asthenosphere. The asthenosphere is part of the mantle, so it's metal-rich rock. It's very warm like the mesosphere, which it surrounds, but because it's shallower, it's under less pressure. And because it's under less pressure, it's a little bit softer, which means it's more easily deformed. So it's solid rock that can deform plastically like the mesosphere, but more easily. And it's in the asthenosphere that in isolated locations, the pressure and temperature are just right for some of the mantle rock to partially melt, which generates molten rock that rises to the surface and results in volcanism. So it's in the asthenosphere, which is a layer of solid rock that in isolated locations, the pressure and temperature are just right for some of the rock to melt and generate magma, which then results in magmatism or volcanism at the surface. And finally, we have the lithosphere. Sorry, I forgot to mention that the asthenosphere, astheno means weak. So this is the weak sphere. So this is that soft, I say it's soft in quotes because it's still rock, but it's the more easily deformed layer of solid rock. Finally, the lithosphere. Lith means rock or stone. So this is the outermost mechanical layer, the layer we live on. It's called a lithosphere because it behaves the way we know rock to behave, right? Because we don't, we think of rock being like plastic, that seems weird to us because we don't interact with rock that's deep inside the earth. But we do interact with this rock. The lithosphere includes the crust and the uppermost part of the mantle. Basically, it's the layer of the outer layer of the earth that's cool enough that's no longer malleable. The rock is no longer deforms plastically. The rock becomes brittle, right? Almost like metal. If you heat up metal, eventually it becomes red hot. It becomes ductile. You can bend it and deform it without it breaking or fracturing. If the metal's just at normal temperature, it's elastic to a point, which means you can bend it and it returns to its original shape. But if you cool it down even more, what happens is the metal becomes brittle. It can break or fracture. And that's what rock in the lithosphere does. It's elastic up to a point. If you deform it, if you put pressure on it, it'll change shape a little bit. But if you deform it enough, it'll crack and fracture. So lithosphere is the cold outer layer of the earth. It's rock, and it can crack and fracture because it's brittle. And it's composed of the crust and the uppermost mantle. So here we can see the chemical layers on the right juxtaposed with the mechanical layers on the left. So we have the metallic core, the iron-rich rock, the mantle, the metal-rich rock of the mantle, and the metal-rich, I misspoke, the metal-poor rock of the crust. And there's two types of crust, the thicker continental crust made up of mostly granite, and the thinner oceanic crust made up of mostly basalt. Then the mechanical layers, we have the solid inner core, the molten outer core. We have the mesosphere, which is solid rock but deforms plastically. It's like a stiff plastic. The asthenosphere, which is this thinner layer, about 250 kilometers thick. It's solid rock, but it deforms plastically like the mesosphere, but it's weaker, so it's soft plastic. And then finally, we have the brittle lithosphere, the outer layer, which includes the crust and the uppermost mantle, the very, 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 very uppermost mantle. And this layer of rock is cool enough where it's brittle, crack and fracture. Those are the chemical layers and the mechanical. At the surface, or near the surface, we can see these layers. We have the crust. We have both oceanic crust, the thin oceanic crust, made mostly of basalt, and the thicker continental crust, mostly of granite. Remember, this is metal poor rock. And so below the crust is the mantle. So this is all mantle rock here. It's all mantle. But mechanically speaking, the crust and the uppermost part of the mantle, this rock is cool enough that it's brittle. And so it makes up the lithosphere. It's the lithosphere. And beneath the lithosphere, if you go deep enough now, this rock is warm enough that it's weak and it deforms plastically. Okay, so it deforms plastically. And so it is part of the asthenosphere. So this is the lithosphere is the rigid, brittle outer layer of the Earth, and the asthenosphere is the malleable, one of the malleable soft layers of the Earth with the mesosphere beneath it. So once the solid Earth was in place, it underwent this process, density stratification, separated by layers. Part of that process is outgassing, where gases that were trapped inside the planet when it's forming, because gases are low density, they started to escape to Earth's surface through volcanoes and volcanic events. And this outgassing is how the atmosphere and the ocean were created, because these gases would be held to Earth's surface by its gravity. And so one of the the large components of these gases was water. So you can see here, this is the concentration of various gases in the atmosphere as a function of time. So this is, today over here, and this is going backward in time in billions of years ago. So 1, 2, 3, 4, 4.5. So the Earth's formations run right here. We just don't have any information about the atmosphere in these early moments, and the atmosphere probably wasn't fully in place. But here we look at the earliest known information about the atmosphere. We have mostly nitrogen, we have a lot of carbon dioxide, and we have a lot of water, right? A lot of water and some methane and ammonia. And as time goes on, you'll see that what happens is the water that's in the atmosphere, which is a lot of it, quickly disappears. Where did that water go? Well, the water vapor condensed out over the course of about 20 million years. What happens is there was these large rainstorms where the water vapor would condense and precipitate. It would fall as precipitation. But the surface of the Earth was so hot that once the liquid water hit the surface, it would just boil back off into the atmosphere. After about 20 million years of this process occurring, the Earth's surface was finally cool enough for liquid water to begin to accumulate. And that was the formation of the ocean. Right? And once the ocean was formed, happens is carbon dioxide was in the atmosphere, it begins to disappear because this carbon dioxide then dissolves into the ocean. Right? And so a lot of this carbon dioxide would be later used by organisms in the process of photosynthesis. So as we'll learn, about 3.5 billion years ago, photosynthetic bacteria, known as cyanobacteria, arrives on the planet, and they use carbon dioxide and water to make, to make their own food. And then later on, about 2.1 billion years ago, algae, photosynthetic algae arrives. But these organisms, the bacteria, the photosynthetic bacteria and algae, they begin to produce oxygen through the process of photosynthesis. Before them, if you notice, there's no oxygen on the planet. So us as animals, we require oxygen to oxidize our food, to metabolize our food. We don't have oxygen, we die. This planet was not a habitable planet to animals to begin with, right? It was only the appearance of these photosynthetic organisms, the bacteria and the algae, that produced the oxygen and oxygenated the atmosphere. And so whenever this is called the oxygen revolution, whenever the atmosphere began to be oxygenated, this set the scene and allowed for the evolution and the appearance and evolution of animal life on the planet. So we owe our existence on this planet to the photosynthetic bacteria and algae from billions of years ago. So Earth is a dynamic planet. It's constantly changing. And why is this? Well, the solid Earth has what's called plate tectonics operating on it. And so plate tectonics, it's a unifying theory, which means that many geological features and events can be explained with the theory of plate tectonics. And plate tectonics helps us understand the composition, internal processes, and the history of Earth on a global scale. Without plate tectonics, we can't explain all these different observations on Earth with a common theory. So plate tectonics is the unifying theory, and it's not that old. Plate tectonics is one of the newest major scientific paradigms. You think of scientific paradigms, you have the atomic structure, chemistry, biological evolution in biology. You have Newtonian physics, quantum mechanics, and relativity in physics. All of those are older than plate tectonics. The theory of plate tectonics really began to come into form in the late 1950s, 1960s, and was widespread accepted by the scientific community in the 1970s. So it's very, very young. So, we've only recently really begun to understand how our planet works as far as plate tectonics goes. Then as the Earth changes, the physical Earth, the solid Earth changes as a result of plate tectonics, life is changing alongside it. Right? So as the Earth changes, life has to change to adapt to it. And the process in which life changes through organic evolution. So the theory of evolution states that all living organisms are related, and they have descended with modification from organisms that lived in the past. So Charles Darwin proposed that the mechanism of evolution is natural selection, which results in the survival of organisms to reproductive age that are best suited for their environments. And so those traits that make them well suited get passed on to the next generation. And then we can see this history of life on the Earth through fossils, which are the remains of once living organisms, and they provide evidence for evolution, and they tell us about the history of life on this planet before humans. Just a quick historical side note, Charles Darwin, at the same time, a gentleman by the name of Sir Alfred Russel Wallace independently came to the idea of evolution driven by natural selection. He was working in Indonesia, where Darwin was in the Galapagos, but Darwin was able to get his paper published in the Royal Academy of Sciences first, and so he gets claim for the theory of evolution. So organic evolution and plate tectonics, these two theories together have changed the way we view our planet. So we can make more sense of its history, knowing the mechanisms through which change occurs on our planet, plate tectonics and organic evolution. And it's through those two major paradigms that we look at the history of the Earth, plate tectonics and organic evolution. Now, geologic time, which is the time of Earth's existence, is quite immense, especially with respect to human timescales, which are, we're used to things on the time frame of seconds, minutes, hours, weeks, months, years, and decades. Where talking about centuries, that's beyond a single human's timescale, right? We don't think on timescale of centuries, let alone millennia, or millions of years, or hundreds of millions of years, or billions of years. So it's hard for us to sometimes comprehend the immensity of geologic time. But that immensity of time, the vast amount of time, is central to understand how Earth changes, because we'll learn that the change on Earth with plate tectonics and evolution is very slow. But even though it's very slow, there's been so much time that slow change can result in dramatic change. And Earth goes through cycles And these cycles are very long, as I mentioned, with respect to human perspective, so they go largely unnoticed to us. And that's why, as I said, we have only recently come to an understanding of how the Earth works, because it's been so hard to wrap our mind around it because it operates so slowly. And geologists use what's known as the geologic timescale, which you'll become familiar with throughout this course, as a calendar to keep track of what happened and when in Earth's history. So this isn't the scale, this figure, but we go all the way back. This is in millions of years, so 4,600 million years, which is 4.6 billion years. And this is 542 million years. So you can see that this right here represents 4.1 billion years. That right there. Where this is only about 0.5 billion years, 500 million years. So the vast majority of Earth's history is in this period of time right here, known as the Precambrian. But how come this part of the timescale, the last 500 million years, is so much more detailed? Well, it's because a notable event occurs about 500 million years ago, what's known as the Cambrian, so notable that the vast majority of Earth time that predates it is known as the Precambrian. Right, so something very significant happens, which we'll talk about later in this course. And that significant event marks the end of this Precambrian and the beginning of the next eon, the Phanerozoic, but it's also more recent, right? So the closer we are to the present, the more information is still around, and so there's more information to be learned, and so we can create a more detailed history. But Earth time is separated into eons. We have the Precambrian and the Phanerozoic, and then we have eras. So we have within the Phanerozoic, we have the Paleozoic era, the Mesozoic era, and the Cenozoic era. And then within the eras, we have periods like the Cambrian, Ordovician, Silurian of the Paleozoic, or the Triassic, Jurassic, Cretaceous of the Mesozoic, the Paleogene, Neogene, or Quaternary of the Cenozoic, right? And then periods are broken down in the Cenozoic even further into epochs, okay? So that's the structure of the geologic timescale. We'll become more familiar with as the semester, as this course goes on. And so, just to finish this introduction, we try to put, Earth history, so the geologic time, map it onto the life of a, say, 45-year-old woman, Mother Earth, where each year of this 45-year-old woman would correspond to 100 million years of geologic time. Okay, so each year is 100 million years. So the first 7 years of her life, so the first 700 million years, are pretty much unaccounted for. We don't know much about what happened. There's too long ago shrouded in history. And then after that, from age 7 to 42, not much happens. All right, it's pretty boring. There's the appearance of bacteria and algae, but nothing really starts going on, starts happening. When she's 42 years old, life comes out of the oceans on continents. She's 45 years old, so within the last year, flowering plants evolved. 8 months ago, the dinosaurs went extinct. Last week, our ancestors, not us, our ancestors evolved. Yesterday, our species evolved. In the last hour, we discovered agriculture and civilization have settled down. And 1 minute ago was the Industrial Revolution. So it kind of puts in perspective, what our history, how our history fits into Earth's history. So if you think of Earth as a 45-year-old woman, we've been around since yesterday, like 1 day out of 45 years. So it's pretty remarkable how insignificant our history is compared to the history of the Earth. But as we'll learn, history of Earth is our history, because everything that happened in all those hundreds of millions of years prior to our evolution set the stage, set the scene for our species to evolve and come to existence on this planet. All right. And to look at the past, we have to use an idea, what's called uniformitarianism, which is a cornerstone in geology. It's a principle that states the laws of nature that we observe today have remained unchanged through time. So thus, processes that we have observed today must have also operated in the past, though maybe at different rates. So it's only through this assumption that we're able to interpret geologic events that are preserved in rock and come to conclusions about what happened in the past. Because we learn about the Earth by observing the processes that are happening today. And if those processes didn't occur in the same way in the past, then we can't make that logical connection from the current observations of rocks today to what happened in the past. So uniformitarianism basically states that the same processes that operate today, like processes involving plate tectonics, organic evolution, and so forth, those also operated in the past, maybe at different rates, a little faster, a little slower, but they operated in the same manner. Now that is an assumption because no one was there in the past. We don't know for sure that they operated in the same way. It seems like a very reasonable assumption, but nonetheless, it is an assumption that must be made. So that is it for our introduction to the course and Earth structure.